Okay, good morning, everyone. So today we will look at the last two techniques. Well, the first of the last two techniques, node voltage analysis and mesh current analysis. Okay, so before we begin those techniques, there are a couple of, well, not a couple actually, there are a few concepts that I want to introduce. So let's go to the right book here. There we go. And okay, superposition principle. Any questions about superposition? So again, superposition principle homework is due in the next few days. Please keep checking the calendar and make sure that you're up to date on all the due dates. Let's see. Okay, these are the concepts that I wanted to talk about. Okay, so for node voltage analysis and mesh current analysis, we'll talk about a few concepts relating to voltages and currents. Okay, so in this illustration here, we have a voltage source and we have is the slide visible to everyone?
Yes.
Okay. So we have 4 resistors and a voltage source Vs. Okay. Now, let's make this a little bit bigger. Each of these voltages, each of these resistors also has a voltage V1, V2, V3, and V4. And there is a reference node at the bottom that is connected to ground. Now, voltage is always measured as the difference in electric potential between 2 points, meaning you measure the electric potential at a point with a reference to some other point in the circuit. Now, more often than not, that reference point is usually the negative end of the power supply or ground. If ground is not explicitly stated or mentioned in the circuit schematic or in the circuit diagram, you can assume the reference point to be the negative end of the power supply, which in this case is right here. And of course, as you can see, ground is also connected to the negative end of the power supply. So this is, again, rather straightforward example. But this is not necessarily true for all circuits. You could have multiple voltage sources in a circuit. You could have voltage sources and current sources. And the ground in the circuit could be somewhere else. So when we begin node voltage analysis, as the name suggests, we are working with voltages. So we need a reference point in that circuit. Okay, so we need a reference point in the circuit. If we say that our reference point is A in this circuit, and we measure the voltages at all the other nodes in the circuit, we can simply state that we are measuring node voltages VB, VC, and VD with reference to VA. And VA would be equal to 0 volts. And because it is a reference node. Again, ground does not necessarily have to be your reference node. Ground does not have to be your reference node, but it makes it easier in most cases, in most circuits. Okay, so wherever your reference node is, that will be 0 volts. If you reference it as a different point other than ground, it does not matter. That reference node will be 0 volts for the purposes of your analysis. Okay, for the purposes of your analysis, that reference node will have a potential of 0 volts. Does that make sense to everyone? Okay. Resistor voltages V1, V2, V3, and V4 are basically measured across the terminals of that resistor. So if we take R1 for instance, now R1 has a voltage V1, and the polarity is shown to us as plus on the left and minus on the right. So you're measuring the voltage V1 across the 2 points of that resistor terminals. The 2 points, basically B and C. So you're measuring VB, VC. And so V1 can be written as the difference in electric potential between VB and VC, where VB, VC, and VD are all node voltages at those particular nodes. So what we are doing is we are expressing each resistor voltage in terms of the node voltages of that circuit. Okay, we're expressing each resistor voltage in terms of the node voltages of that circuit. And our job is to determine the values of these node voltages. And that, in essence, is node voltage analysis. Okay, so think over it for 10 seconds. Let me know if anyone has any questions. Yes. So the question being asked is, why is node voltage expressed as a single subscript, right? VA, VB, VC, VD. So if we think back to chapter 1, it's a good question. Voltages always use a 2 subscript notation. Currents also typically use a 2 subscript notation if we want to express it between 2 points. So in voltage, if the second subscript is missing, then it is automatically assumed that it's ground. But the point I want to make clear is when we perform node voltage analysis, the reference point would be some other node other than ground. So when we say VB, VC, and VD in this circuit, we are measuring with respect to A. It just so happens that A is connected to ground. Okay, but your reference node could be any node in the circuit. Reference node can be any node in the circuit. So for example, if I wish to, I could say B is my reference node. Now that reference node is the negative end of my measurement for all other nodes in the circuit. So I could measure VA, and what I would be measuring is voltage at A with reference to B. If I measured VC, I would be measuring voltage at C with reference to B. VD would mean I'm measuring voltage at D with reference to B, where B, because it is the reference node, is considered to have 0 volts. Now, even though A is connected to ground, the positive reference of my voltage measurement will be at A, and negative would be at B. Again, think over it. Let me know if anyone has any questions. These are just some of the concepts that I found historically students have some trouble with. Did that make sense? And again, of course, as with anything, the more we look at it, the more problems we solve. When we look at an example problem, it'll start to make more sense. Any questions? Any questions at all? Yes. 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 Well, for the purposes of analysis, we can ignore the ground. We can ignore the ground. It makes sense to use one end of the voltage source as the reference. Because what happens? Voltage is measured between 2 points. If we choose either B or A as reference, the voltage between A and B is given by the voltage source Vs. Does that make sense? So in a circuit, if you're analyzing using node voltage analysis, if we have a voltage source in a circuit, and it will make the most sense to choose one end of the voltage source as the reference node. If we choose A as a reference, then VB is automatically Vs. If B is the reference, then VA would be minus Vs. Does that make sense to everyone? Right, because you're looking plus and minus for Vs, but our reference for the voltage is flipped. And so it should just be minus Vs. So automatically, again, remember, we are solving for the voltages present at each node in the circuit, meaning those are the unknown variables, right? So if we choose one end of the voltage source as the reference, we automatically eliminate one variable from our analysis. So we only have to analyze for two variables, VC and VD. And so, again, we'll talk about this when we actually get to node voltage analysis. But as concepts, I want to make sure students understand that what we are doing in that analysis is we are expressing each resistor voltage in terms of the node voltages at either end of those resistors. Then we solve for all of the node voltages in the circuit. Once we have the answers for the node voltages, we can easily calculate all of the resistor voltages in the circuit. Once we have the resistor voltages, we can calculate the resistor currents, right? And that is node voltage analysis. Now, so similarly, here, V2 can be expressed as the difference between VC and VA. V3 is between VC and VD. And V4 is VD and VA, right? Because your reference is all at A. And the resistor voltages, basically, again, just look at the terminals, see which nodes they're connected to, assume the polarity of the voltages, and then higher voltage or higher polarity minus the lower one. So that is node voltage analysis, the concepts for node voltage analysis. For mesh current analysis, it's a little different. You're all familiar with branch currents, right? So a current that flows through a particular branch of a circuit is known as the branch current. These are the actual currents that are flowing in a circuit. So for Vs, I could say maybe the current flowing through Vs is Is. Current flowing through R1, I could label as I1. I3, I4, and I2. Now, the current directions are assumed, but the assumption is based on logic, right? For the power supply, voltage supply Vs, current will always go from minus to plus, so it's going up in the upwards direction. When it goes up, it only has one pathway to flow through, meaning through R1, going from left to right, and then to all the resistors. So all of the current directions are assumed. Okay, so all of these are branch currents. So let me write it down here. All of these are branch currents. Is, I1, I2, I3, and I4. Assumed direction, but the assumption is based on logic. And doesn't really matter if you choose the opposite direction. Your analysis will turn, as long as you're consistent within the analysis, your answer will always be correct. So it doesn't matter if I choose the opposite direction. Okay, so those are all branch currents. Mesh currents is basically a hypothetical current that we assume for the purposes of analysis. Okay, so mesh currents are not real. Mesh currents are purely hypothetical or theoretical. Mesh currents are not real. They're theoretical. A mesh in an electrical circuit is simply a closed pathway. It is also described as a simple loop. A loop that does not have any other loops inside it. Okay, simple loop that does not have any other loop inside it. So what's the difference between a mesh and a loop? Well, an electrical loop is basically, again, any closed pathway, right? You start from point A, you go around the circuit, and you come back to point A. That is an electrical loop. So if you take a look at this circuit, electrical loop starting from point A at the bottom can be this one on the left, can be this one on the right, or it could be the outer one. Make sense? So you have 3 electrical loops in there, right? The outer loop has 2 loops inside it. Make sense? So a mesh is a simple loop that does not have any other loop inside it, meaning this one and this one is a simple loop because it does not have another loop inside it, and it's simply a mesh. So identifying a mesh is relatively straightforward. You take a closed pathway, and if it doesn't have any other pathway inside it, that's a mesh. Okay, so in this case, we can say this is mesh 1, this is mesh 2. Okay, M1 and M2 are meshes. And the current that flows inside that mesh is known as the mesh current. Now, mesh currents are completely hypothetical. It's you who's going to choose the direction of the mesh current, either clockwise or counterclockwise. So mesh currents are theoretical. Assume clockwise direction or clockwise flow or counterclockwise flow. It's up to you. It does not really matter. Okay, it does not really matter. Now, when you assume a mesh current, these are mesh currents, IA and IB. Is a mesh current. Okay. Now, when you have mesh currents in that mesh flowing through the resistor, it causes a voltage drop, right? So now you express each resistor voltage in terms of that mesh current. And then we apply KVL and add up all the voltages around that mesh. Okay, the point of analysis is to write mathematical equations so we can solve for unknown variables. And so the more equations we write, the easier it gets for us to analyze a circuit. So in this case, we only have 2 meshes. So we have mesh current IA and mesh current IB. Both of them are flowing in a clockwise direction. You take each mesh, apply KVL around the loop. Each mesh current causes a voltage drop across the resistors. You add up all those resistor voltages, and you have your equation. Think on it for 10 seconds. Let me know if you have any questions. Yes. There is, but there are cases when you would apply a KVL around that outer loop, but that again, we'll look at it in detail when we do mesh current analysis. Yeah.
So would IB ever be able to be counterclockwise as IA was clockwise?
It doesn't actually matter which direction we take, IA or IB. We can take both of them clockwise or both of them counterclockwise, or one of them clockwise, the other one counterclockwise, and it actually does not matter at all. In all cases, if we stick with our assumption, meaning if we write a KVL equation for mesh one, we keep the assumptions constant when we move to the next mesh. So we do not, so once we make an assumption at the beginning of our analysis, we stick with it. We do not change our assumptions halfway through our problem. Does that make sense to everyone?
Yes.
So that is what I mean when I say, as long as you're consistent within your analysis. You assume a direction at the beginning, and then you stick with it till the end. And then you get the correct equations, and you'll have the right answer at the end. Okay. Now, obviously, as I said, these are hypothetical currents. So there is one point I want to make, which is resistor R2. R2 is a shared branch. So we see there are two mesh currents flowing through that circuit, which is physically impossible. You cannot have two currents flowing in the circuit at the same time. Okay, current is a result of the difference in electric potential between 2 points. So if we say one point is higher than the other, the current flows from the higher point to the lower point, plus to minus. At the same time, I cannot say that the other point is higher than the, if A is higher, then B has to be lower. And if B is higher, then A has to be lower. Both cannot be true at the same time, right? And so mesh currents are completely hypothetical. Branch currents are real. Okay, branch currents are real. Mesh currents are hypothetical. All right. Yes. Branch currents is the superposition of all the meshes. Yes and no. If it is a shared branch, then yes, I think I see your point. Is basically it's either the sum or the difference of the currents in that shared branch. But if the branch is not shared, like with R1, R3, and R4, it's not shared. You only have one mesh current flowing through there, right? So the branch current in there would be exactly the same as the mesh current. Yeah. Okay. So for node voltage analysis, what we need to do is we take, any other questions from anyone about any of these concepts before I move on? Okay. All right. So for node voltage analysis, what we need to do is, again, the whole point or purpose of these analysis techniques is so that we can solve for the unknown voltages and currents mathematically, meaning we need to write mathematical equations. We want to generate equations by applying either KVL or KCL. So for node voltage analysis, we are going to apply KCL. Okay, for node voltage analysis, we need to apply KCL and generate our equations. Okay, so we have to assume branch currents, assume direction, then we apply KCL at different nodes. Once you apply KCL, we express each current in terms of the resistor voltages, then express each resistor voltage in terms of the node voltages, reduce it by plugging in all the known values, and then generate our equations. And then, of course, solve for the unknown variables. So as a first step, what you need to do is, if you have a resistor like this, R, you assume a direction of current. So you assume a direction of current. And in this case, I'm assuming I going from left to right. Now, the assumption does not matter. You could assume I going from right to left. Okay, it does not matter. But again, whatever assumption you make, you have to stick with it till the end of your problem. Now, the important point is, if my current I is going from left to right, which end is higher, VA or VB? VA is higher, right? So VA is plus, VB is minus. So when I express my resistor voltage VR, I would write in terms of the node voltages, it is VA minus VB. Make sense to everyone? Higher voltage, right? VA minus VB. Then I apply Ohm's law and I express the current I in terms of that resistor voltage VR over R. And then you plug in VR in terms of the node voltages. So VA minus VB divided by R. The value of R would be known to us. Let's say it is 10 ohms, for instance. R is equal to 10 ohms, and I plug that in, I would get I is equal to 0.1 VA minus 0.1 VB. You get a set of linear equations, standard equations, algebra, simultaneous equations. You solve them with any method that you choose, and you get the answers for VA and VB. Now, this is just the first step, right? This is just the first step, just showing how you need to express the resistor voltages. So these are the steps you would take to express each resistor voltage in terms of the node voltages. Okay. First, we assume a direction for the current, the branch current. Then we express each resistor, each branch current in terms of the resistor voltage by applying Ohm's law. We express each resistor voltage in terms of the node voltages. Plug in all the node values, and then you reduce the equation or reduce the expression. Does that make sense to everyone? So if you take a look at the second image, you have three resistors, R1, R2, and R3, with the assumed current directions for I1, I2, and I3. What we're going to do is we're going to apply KCL at node B. So you apply KCL at node B. We obtain I1 is equal to I2 plus I3, right? One current entering and two currents leaving. So I1 enters, I2 and I3 leave. Then I express I1 in terms of the resistor voltage. So I would say VR1 divided by R1. I have VR2 divided by R2 and VR3 divided by R3. Since I1 is going from the left, I'm going to say this is higher than B. Since R3 is also going from left to right, VB is higher than VD. And for I2, VB is higher than VC. Okay. So the polarity of the resistor voltages comes from the fact, comes from the assumed direction of our current, of the branch currents. Now, one question students typically ask is, how come there are three different polarities at node B? Okay, so the three different signs that you see at node B right here are with reference to the other points. Meaning, if I compare the voltage at B to the voltage at A, then it is minus, meaning it is lower than A. Then if I compare B to C, then it is higher than C. And if I compare B to D, then B is again higher than D. So that's why you have three different signs at that node. But all those three signs are with reference to some other points in the circuit. Okay, they are not related to each other. That's why you have a minus and a plus at the same place. But those minus and plus are not related. They are, plus is for some other node and the minus is for some other node. Does that make sense? Right? Okay, so VR1 is basically VA minus VB VR2 is VB minus VC and VR3 is VB minus VD. And that's it. These are the steps for node voltage analysis. I have 4 unknown variables, A, B, C, D, VA, VB, VC, VD. One of them would be my reference node. Doesn't matter which one it is, right? So that reference node will always be 0. So I eliminated one of the unknowns, right? If I take C as my reference, VC would be equal to 0. Then the only unknowns left in the circuit are A, B, and D, VA, VB, and VD. If I have 3 unknowns, I need at least 3 equations to solve for those 3 unknowns. Yes. Depends on the circuit. Yeah. So the question being asked is, would it make sense to set B as the reference node? It's absolutely. It depends on the circuit, and we can choose B as the reference node. Yes. Yeah. Okay. Any other questions from anyone?
If we can do some of the analysis with equivalent resistance and simpler tools, is it okay to do that and then combine that with known voltage analysis?
Could you repeat the question? Combine.
If we can use simpler tools from things like equivalent resistance, is that
Oh,
okay
I see
to
what you're
use?
saying. That depends on if the circuit has combinable resistances or not. So if it does have it, then yes, we can combine it to simplify at the beginning. But then if the problem asks students to solve using node voltage analysis, then the primary assessment has to be about node voltage analysis. Students cannot solve it using another technique. Then I would have no basis for judgment. I would have no basis for assessment. So I would not be able to award credit. So even if your answers are correct, and that goes for any particular question, if I ask a specific method of analysis, then students have to show that method. Otherwise, I'm not assessing your knowledge about that topic, right? And so I would not be able to award any credit for that. You can, but to answer your original question, if there are 2 resistors in series or parallel, and we want to reduce it before we begin analysis, that is absolutely fine. Let me see, I think in the example that I have, so in this example, yes. So in this example, R2 and R3 are in parallel, and so I will talk about that. Okay, so this is just a summary of the steps, node voltage analysis. The first thing we do is identify all the nodes, and you select a reference node. More often than not, if you have a voltage source, choose one end of the source as reference node. One end of the voltage source. Let me put it that way. One end of voltage source as your reference. Automatically gives you so it automatically gives you the node voltage at the other end of the source, right? If you take the negative end of the source as your reference, then the other end of the source is the value of Vs or whatever the source voltage is, right? So the first thing to do is to choose a reference node in the circuit, and you assign branch currents to all the branches, assume direction. So you assume the direction, doesn't matter what the direction is, as long as it makes logical sense. Well, even if it doesn't make logical sense, your answer will still be correct at the end, right? So if you apply KCL at one node and the current's actually flowing from plus to minus for a source, you would have to take the same direction for all the other equations. So your answers will always turn out to be correct. So again, assumed direction does not actually matter. Then you apply KCL at each node. Once you have your KCL equation, you apply Ohm's law and express each branch current in terms of the resistor voltages. And then you express each resistor voltage in terms of the node voltages. And after this, I would say step 6, plug in all known values and reduce the expression. Reduce the expression, right? Linear expression. So in terms of your variables, you have the node voltages, and then you have some constants in front of it. From that point on, you can solve it with any method you want. Simultaneous equation, solve it by hand. If you have a programmable calculator, program it into your calculators, determinants, Cramer's rule, matrix, any method that you're comfortable with. Okay, questions? Any questions at all? Okay. Let's look at this example. Circuit has two current sources. Both the values are given. You have 4 resistors. All 4 resistor values are given. If you look at R2 and R3, they are in parallel. This is the exact same node. There's nothing else connected between any of these terminals. And this is the exact same node. So identify all the nodes in the circuit. Identify all the nodes in the circuit. Right? I could draw the circuit like this. And then, oh. Oh, going up. And this one's going down. Okay, so you can see there's only 3 nodes in the circuit. Let me call this node A, or actually just A, B, and C. And since ground is conveniently marked for us, I'm going to take node C as my reference. So if I take node C as my reference, that means VC for the purposes of my analysis is equal to 0 volts. Also, R2 and R3 are in parallel. So I can combine those two together to have just one single resistance. So this answers the other question. Can we use some other techniques, before we begin analysis? So then you can absolutely do that. Right? R2 and R3 are in parallel. You can combine it into one single resistance. And we can call it R5. R5 is R2 in parallel with R3. The value should be, is it 2K and 10K? It's 20 divided by, 12? So 1.667 kilo ohms. $1.66K. Then I have current source I1. Now, I want to assume a direction of the current, but I particularly like this problem because it, well, you will see the answers is going to be a little different. In this case, I1 is going up and I2 is going down. So it makes logical sense to choose R5 or IR5 as going from left to right, right? So I'm going to label it as IR5. Okay, IR5. So keep writing away. Then for IR1, I will choose going down. And for IR4, let's choose, well, let's choose going down. Again, it does not actually matter. Okay, it's not actually matter what we choose. A, B, and C. So now if I apply KCL at node A, KCL at A, I get I1 entering, IR5 leaving, and I have IR1 also as leaving. Right, so my KCL expression becomes I1. What is going on? I1 is equal to IR5 plus IR1. IR5, I can write as VA minus VB divided by R5, and IR1 would be VA minus VC divided by R1. Does everyone see that? Okay, something's going on, and as soon as I write, it's getting wiped out. Don't know why. Okay, let's hope it stays stable now. So 10 milliamps. And then I have VA minus VB divided by R5. R5 was 166.67. VC is 0, so it simply becomes VA over R1. R1 is 1000. I reduce it and I get, what do I get? I have to perform 1.667 times. This gives me, this will be 0.01. Six VB plus VA. Reduce the expression, and I would get what I would get. 6 VA that is your first equation. You could also, of course, multiply it with like 10,000 just to get, if you don't want to work in decimals. Okay, time is up for today. Let's see if I want to. Yeah, let's just stop here. I'll complete this on Friday, and then we'll also look into mesh current analysis and wrap up mesh current analysis on Friday. Okay, so let's just do that. All right. I will be available in the office, office hours right after class at 11. And then again, later today, I'll be in the lab from 3 to 6. So if you have any questions, send me an email, stop by, and I'd be happy to see you. All right. We'll see you all Friday.
Can I ask a quick question?
Yes.
I'm in your lab, and for the pre-lab, it's on node voltage. And I found all the node voltage